So all those surface area ones that you did so far all had circular cross sections. So if you were to slice them across their perpendicular to their axis, they would all be slices that were, circles. So today we're going to do other shapes of cross sections. They still will be known shapes, so triangles, rectangles, diamonds, which are really just a parallelogram. So, but they all will have regular cross-section shapes. Okay, what will be fixed about it is the base. So what we need to do is to be able to visualize a fixed base. So what we're going to do is rotate our axis into 3 dimensions, and we're going to take a parabola, which we'd been graphing in 2D, and we're going to lie it down into 3 dimensions and have it become the base of an object that we are going to find the volume of. Okay, so for example, let's start with this parabola. Okay, we know that parabola to be x equals y squared. We also know it to be y equals plus or minus the square root of x. Okay, so that's the same definition of that parabola. What we want to do now is take that same parabola and try and draw it in perspective as if it is lying down. Okay, so here's still our x-axis, here's our y-axis, so now the parabola looks like that. Okay, so we're trying to lie that flat. I'm going to extend my upper one a little bit because we're going to stop this parabola at 3, x is 3, and so I want to draw something parallel to the y-axis. So let's see how I can do here. Okay. All right, so that parabola is now going to be the base of a 3-dimensional object. All right, so the y values are 3 and -3, which means what's the x value on my x-axis? How far have I come? Out to 9. Okay. The shape we're going to create from this fixed base are rectangles. And so the rectangle is going to use this as its bottom, and then we're going to come straight up and draw a rectangle that's rising up from the edge in such a way that the height is twice as tall as the base. All right, so I'm going to write this out so you've got it in your notes. So consider x equals y squared as the base for rectangular cross sections whose height is twice its width on the interval 0 to 9. And then the directions are find the volume. All right, so that's the question. Let's get a good drawing of this. So this is the biggest rectangle here on the end. This rectangle at the end has a base of how much? Going from corner to corner, okay? The base has a length of 6 going from corner to corner, which means that end rectangle has a height of what? 12, right? If it's twice the height of 12. So that single rectangle has an area of 72 square units. That's the largest rectangle. But there are a whole bunch of rectangles stacked immediately behind that. Each rectangle getting successively smaller as we go backwards. So I'm going to try and draw some rectangles behind that. Okay, come on. So there's a rectangle behind, and it's slightly smaller. And then there's a rectangle behind that, and that's slightly smaller still. And the rectangles just keep getting smaller the farther you go back. This ultimately reminds me of a wedge of cheese. And as you slice it, it's like cheese slices that come off. The cheese slices just keep getting smaller the farther back that you go back towards the origin. Okay? Oops. All right. Okay, are you able to picture that? Okay, so what our job is to find something to describe the area of an arbitrary wedge, not just the end wedge. The end wedge is 6 by 12, but we want to pick any random slice in there and to be able to describe its rectangle. So if you could with me, let's focus on this last one that I just drew. I'm going to make it green. Well, as the base of the parabola gets more narrow, okay, because then that means the bottom of every rectangle gets more narrow, and which means the rectangles all get smaller and smaller. So this is going to eventually come down to a little point on the end.
Oh, it's because we're rotating.
We're not rotating anything. Just each of these rectangles, their bases like that, their bases continue to get to deep.
The bases are, like, no matter where it's at, the base is always half the height.
Right, no matter where. And the base is always between the two edges of the parabola. And so as the two edges of the parabola narrow and get closer to each other, that base gets smaller and smaller, so the height gets smaller and smaller, and eventually this whole thing will be vanishing down to nothingness. So let's pick arbitrarily this one rectangle, which I'm sorry, my perspective really is not, this does not look like the base and the height are in ratio 2 to 1, so I apologize for that. But let's pick an arbitrary one, all right? So let's say that this is point A on the x-axis, somewhere between 0 and 9, that is point A. If that's point A, where are the end points, the end corners of that rectangle? Not 2A, because A measures this way. A measures from the origin. A is going from, this is A. Okay? So then how wide is it from here to here? Okay? Well, let's, again, remember here, this was 9, but you said this was 6 and 6. Okay? How did you know that? Well, 9 goes from here to here, and then how far was this? 3, and how far was that? 3. How'd you come up with 3? Okay, so if this from here to here is A, then from here to here is the square root of A, in which the other one is also the square root of A. And so we know that this is the square root of A, and this is the negative square root of A. So how long is the base of that particular arbitrary rectangle? 2 square root A. And by definition, how tall will that particular rectangle be, even though my scale is not great? It will be double that, so 4 rad A. And what will the area be of that single particular rectangle? 8A. Right, does that match like what we did at the end? We said our last rectangle, the biggest rectangle at the end, had an area of 72 because it was 6 by 12. But if we did it by the formula here, 8A, what is the A value of that final rectangle? 9. So 8 times 9 is 72. Okay, so that confirms that that is the area. So every single thin little slice here of the cross section will have an area of 8A, depending on what A is. So the way we're going to use calculus to get all of the area is that we say we want to take the limit of the sum of all of those 8A rectangles. As k goes from 1 to n, and n goes to infinity. Okay, that is the sum of infinitely many paper-thin rectangles, all of whom area is 8A. If we could add up all of their areas, then we would have the volume. And so we now know that that could be better written in calculus as the integral of 8A dA going from 0 to 9. And then the hardest part is the setup. Once you've got the setup, the calculus is going to be a breeze. Okay, the antiderivative of that is 4a squared plus the constant c going from 0 to 9. Therefore, it'll be 4 times 9 squared, or 4 times 81, or 324 cubic units cubed. And that represents the cubic unit volume of that wedge shape.
I have a question about the limit notation.
Okay.
Why is n to limit of n to the not n to the 9?
Okay, because we don't want just 9 rectangles.
Yeah.
We want infinitely many rectangles. In limit notation, I'll put k here. Oops.
So where does
Because then you would say on 0 to 9. I mean, you don't, it's not part of the limit notation, it's just separate on the bounds. There is no, the bounds are not part of the limit notation. Okay, the limit notation is describing the number of rectangles that there are. There are always going to be infinitely many rectangles no matter what the bounds are. If my bounds were 0 to 1, I still have infinitely many rectangles. If my bounds are 0 to 100, I still have infinitely many rectangles. Okay, the bounds are just going to, the interval would be stated separately. Okay. Okay, any questions on that one? Okay, let's try another one. Same base, different shape. All right, same base with square cross sections whose diagonals are within the base. What was that for, Jerry? It's not just a square. It's like a diamond. All right, so yeah, let's picture what we've got here. All right, these are squares but their diagonals are within the base. And so the green line I'm drawing right now is the diagonal of a square. That means that part of the square is above. Let's see how I can do this well. Part of the square is above, and part of the square is below. You can, yeah, the z-axis would be here, if you like. Okay, there's your z-axis if you like. X-axis, y-axis, z-axis. Okay, so we've got a diagonal running through here. And all such diagonals, so we know our end square has a diagonal length of 6. In a square that connects to the side edges. Well, we can figure out the geometry on that because we know that the diagonal cuts this into a 45-degree isosceles triangle. Okay, we know because this is a square that this is a right angle, this is a right angle, and the other angles are both 45 degrees. So we've got an isosceles right triangle. All right, so let's pick an arbitrary square. So let's say that this is out at position A. The corners are still going to be rad A and negative rad A according to this equation. And so the diagonal length is a length of 2 rad A. How does the diagonal length connect to the length of the individual sides? How can we figure that out? We can do Pythagorean theorem for sure. All right, so let's call the individual sides side S. And so according to the Pythagorean theorem, we know that S squared plus S squared has to equal the hypotenuse, which is 2 rad A quantity squared, which means 2S squared equals 4A, which means S squared is 2A, and a single side is the square root of the quantity 2A. And so one side of the square has a length of 2A. All sides of the square actually have a length of rad 2A. So then I can find the area. Yeah, so the area would be, in a square, rad 2A, quantity squared, which is 2A. So the geometry is going to be where you're going to do most of your work. Your heavy lifting is going to come in your geometry. Okay, the easy part of your workout will be then setting up the volume, because the definition of the volume is the integral along the interval 0 to 9 of the area. So 2A dA. So such an easy problem to do once you've got the geometry worked out. So the antiderivative is A squared plus C on 0 to 9. And so then the answer is 81 cubic units again. Say that again.